So, hello everybody. My name is Chris Swinburn from Beyond Carbon. Today we're going to be talking about airtightness for high performance buildings. Very briefly about us, there are 12 of us in Beyond Carbon. We started in 2022 with a mission for delivering low energy, healthy buildings and making that normal practice. Out of those 12 people, the vast majority are Passivhaus consultants, and that is our main area of expertise. In delivering low energy buildings, we think the Passivhaus standard is really fundamental to that. We only really work on large scale projects, so typically multi-residential projects, but also offices, student accommodation, and so on. So only kind of at scale. And this presentation is going to focus on large scale construction techniques and building practice. So the context here is climate change, and many now believe that this 1.5 degrees of global warming is probably going to be surpassed. But nevertheless, it remains, as a business, our target to be doing our bit to minimize climate change through the built environment and to keep this number as low as possible. Why this is relevant to construction, you may remember these sorts of statistics that around 42% of UK carbon emissions are attributed to the built environment. Of that, a significant proportion are related to space heating and cooling demand. And this is really being picked up in the latest sort of industry standards for energy performance of buildings. So REBA, for example, in their which is now their Sustainable Outcomes Guide, pick up energy targets, and there's a big emphasis on fabric first. If you go to LETI, you start to get into the arena of space heating targets, and which really point you towards Passivhaus levels of performance. Down at very low energy levels of performance, like you get with Passivhaus, airtightness becomes a really fundamental thing. So on the left here, we have the impact of airtightness on space heating for a building regs building, and on the right, at Passivhaus airtightness, you can see the importance of being able to squeeze that infiltration heat loss right down. So there's an energy efficiency reason why we want to tackle infiltration as a climate change reason. We've just used the term infiltration, and what do we mean by that? Well, actually, these terms get used a little bit loosely. Infiltration is technically air entering a building in an uncontrolled way, unconditioned air from outside. So in the winter, that's going to cause heat loss, cold drafts. In the summer, that's going to cause potentially heat gains. Exfiltration is the kind of parallel process to that, which is air leaving the building, and both are sort of happening at the same time. And exfiltration has other implications, namely around moisture and fabric protection. But when we talk about infiltration, airtightness, we're talking about all of this, so air movement, uncontrolled air movement through a building. I mentioned the potential for cold drafts in winter, and airtightness and comfort are very much linked. This chart just shows you the relationship between air speeds and a feeling of a cold draft. And actually, you think about an airspeed of 0.1 meters per second, that's pretty slow moving. Anything above that, and you are starting to get cold drafts being felt. You can easily get these sorts of air velocities as a result of infiltration into the building. So there's a thermal comfort issue with airtightness that we're looking to address. You can't necessarily see airtightness. You can't necessarily even feel it in an average sort of condition, average winter conditions. It tends to be when you exaggerate those conditions with air pressure testing and things like thermography, that you can really see it and visualize it. Protection of building fabric, this is again related to infiltration, but more specifically exfiltration. So when you have moist air traveling through the facade of your building from the inside, it is carrying with it moisture. And at some point in that facade, it will reach dew point and it will deposit some of that moisture as condensation. And that's obviously a potential problem. If that moisture can't escape, you have moisture buildup. You don't want moisture building up in your structure, and it can also lead to mold formation. In the worst case, it can lead to structural damage. So Air tightness and minimizing infiltration is also connected to protecting the building fabric itself and longevity of buildings. A question is often put, particularly for Passivhaus buildings, is surely at very low infiltration rates, if you make the building too airtight, are people going to suffocate? Are they going to run out of oxygen? Well, this chart just illustrates that actually the amount of air you need for breathing is really tiny, and even Passivhaus infiltration rates are sufficient to cover that amount of airflow through the building that would meet those requirements. Much more significant are the requirements of how you minimize moisture, VOCs, odors. You need a lot more air for that, and that's where what you want to have is controlled mechanical ventilation, which is something that Passivhaus would naturally give you as part of the standard. So just to distinguish here between infiltration is uncontrolled, variable. Ventilation is something that should be intentional and controlled and meet a specific requirement and should also be energy efficient. So we're talking about a different topic here, and we shouldn't be relying on infiltration to ventilate our buildings. There is another implication of having poor air tightness, which is when you have heat recovery ventilation, having a poor air tightness can reduce the efficiency of those systems. And one way to illustrate this is just to think about what happens to the air that's supplied from a heat recovery unit, from an MVHR. Effectively, what you're doing is you're slightly pressurizing a room that you put that air into. And on the other hand, if you're extracting air from a bathroom or kitchen, you're slightly depressurizing that room. Those small changes in pressure in an airtight building, in a building which is not airtight, will result in potential leakage, because essentially the skin of the building is so leaky that even a small increase in pressure will push air out of the building, and on the other side, on the extract side, will pull air into the building. What then happens is effectively you negate some of your heat recovery, because actually you're not transferring air within your heat exchanger, you're actually pulling in cold air from outside or losing warm air to outside, and then having to heat that air up with your heating system. So air tightness and MVHR go hand in hand, and we typically might suggest that an air tightness below 3 was the kind of the maximum number you would want before for an MVHR to work efficiently, though that's not a straightforward relationship. So how do we measure air tightness? Well, the key thing is you can measure air tightness, but you can't measure infiltration. So infiltration is the thing we're really interested in. How much air across the winter is moving through the building and how much energy is required to heat that air up. You can't measure that. What you can do is measure air tightness by effectively exaggerating the air leakage through a building by pressurizing it. So you strap what's called a blower door fan onto an opening of the building, typically a door, could be a window, and you pump air into the building, or indeed extract air from the building to depressurize it. Both of those tests are important for different reasons, and you would want to do both of those certainly for a Passivhaus building. But the point is you're exaggerating the air leakage through the building by applying pressure. And there are two metrics that you could use for describing the air leakage of the building. The terms that we use, and there's no set way of using these exactly, but air permeability is the most common one that's used for building regulations, things like BREEAM, and that is the airflow across the skin of the building per meter squared of that skin, so of that envelope, at 50 pascals pressure when pressurized with a fan. That's permeability, and it's a sort of measure of the leakage per meter squared of your envelope. The other one is what we call air leakage, which is what's used for Passivhaus, which is in air changes per hour. So that's the number of times the volume of the buildings, the volume of the building is sort of replaced with air during that pressure test at 50 pascals. The numbers from these differ from each other, and that relationship depends on the size of the building. Typically for very large buildings, which is the subject really of this presentation, the air changes per hour comes out as a lower figure than the air permeability. So they do differ. They're a different metric, and that's important for larger buildings. So what air tightness levels are we talking about here? How do we define these? Well, we try to define this in really physical terms because it helps people just to kind of get a feel for this. These dots are sort of representation of the amount of equivalent hole you would have for certain levels of air tightness per meter squared of facade. So if you took a 1 by 1 meter square of the envelope, taking a passive house building, you would expect to see a single 8mm diameter hole per meter squared. That would give the equivalent air leakage. Whereas you go all the way to building regs typical in the middle there, that will be more like 5 of those 8mm diameter holes. And then an old leaky building, if you like, would be 20 of those holes. So what does that actually look like? Well, that would look like this. And this is what we find quite extraordinary, is if you, every meter squared of your building, and it was a passive house, for every meter squared, you had a 8mm diameter hole, which you would be able to see visible light through. You would certainly notice looking around your building envelope from the inside. I think you'd be pretty shocked to find that. That doesn't strike as very good construction quality, but that is the equivalent in hole size that would give passive house levels of air tightness, which makes us think that that surely can't be that difficult to achieve. Of course, the reality is that we're not talking about holes of 8mm per meter squared of facade. We're talking about the summation of all the imperfections in the building, particularly things like windows and doors that are imperfect by nature. They have seals that are not perfect, and then maybe where there's junctions that were not perfectly sealed. You add all those together, and in principle, you would be getting an equivalent to an 8mm diameter hole per meter squared. So we feel that still gives confidence that this surely must be achievable with the right level of workmanship, good quality windows, with your junctions properly designed and properly constructed. This to us does not feel like an impossible feat at all. Building regulations would be 10 of those. So you can see the kind of difference. That's quite extraordinary. And what is the difference between those two? A lot of the difference is planning and good execution. So how do we design an airtight building? How do we get to that level of super air tightness that we see in a passive house building? Well, the formula we like to use is this, that simply air tightness is the result of robust design and the workmanship on site. If those two things are done well, then there's every reason to think you can get passive house air tightness, and that's been proved by all the passive house buildings that have been constructed to date. The robust design element, I'm going to go into a little bit more detail. There's 4 kind of elements that are part of that are essential to that. The first is airtight materials. So the materials in your design are actually airtight. They're using quality products, for example, tapes, windows. The air barrier is continuous, and it actually does indeed join it up all the way around your junction in 3 dimensions, not just 2. And then it's buildable, which means that the workmanship standards can be reasonable. You're not expecting workmanship standards that are far higher than your average construction team could provide. If you tick those boxes, then that is a robust design. The thing with airtightness is that you have to think in these binary terms. Airtightness is not something you can simply judge based on a construction detail and say, is it a 1, is it a 3, is it a 5? No, the way we see this is binary. It's either airtight or it's not. And if it hits those boxes, ticks those boxes in that list, then we can say, yes, this is airtight, and the performance will be extremely good, and we should end up with a building overall which is meeting the passive house kind of levels of airtightness. Target zero is what this is about. Think about this in health and safety terms. No one targets a number of accidents that are acceptable. The focus is 0, and that's kind of the approach you need to have with airtightness. You need to make sure that all parts of design are essentially completely airtight. And then you will see that being delivered in practice. In terms of the overall flow of a project, then this top line is sort of the design stage. You are starting with a strategy and you're developing drawings, you're choosing products, you're reviewing. There's an iterative process until you get to that airtight design point. Then when it goes to site, there's a similar process of the installation, quality monitoring, and a bit of a feedback loop for some preliminary testing. So you get to a final test and your certificate. So there's a flow to this. The key points, though, are getting this airtight design right, and then we'll come on to later the construction process, the testing process, and quality monitoring, and how that ensures you achieve that on site. This is a very helpful diagram for the Passivhaus Trust. Really quite a simple idea here that the more airtight your buildings, so going left on the x-axis, the harder, of course, it is to deliver. So y-axis is difficulty. If you don't have a plan, if there isn't a strategy, then that difficulty gets exponentially higher as you get towards more airtight buildings. But if there is a strategy, then yes, of course, it is still harder, but that line is much flatter. You're able to much more likely to be able to deliver that airtightness strategy if it's well thought through and planned. And we see this on buildings that are building regs compliant, that they might achieve a 10, they might achieve a 5. We don't know what they're really going to get. If you're really lucky, you might get slightly lower. But you're in a kind of area of uncertainty and difficulty. But with a plan, that uncertainty is dramatically reduced. So strategic basics for airtightness. This is a useful diagram. It's only a kind of rule of thumb, and these rules can certainly be stretched and should be stretched. But a simple idea here is that the airtight layer should be on the inside of your insulation. That is the most robust, best practice way to ensure you don't have problems with moisture, because you don't want moist air passing through your insulation zone to a point where it might start to drop out its moisture and cause mold and condensation issues. So that is the best practice. Your insulation zone is on the outside of that, and then there's your weatherproofing and a windproof layer on the outside to prevent from thermal bypass. But the key thing is that red line on the inside of the insulation zone. And the other key thing is the services zone being well away from that red line. You don't want your services weaving in and out of your airtight layer. And the structural zone being on the inside of that layer. Now, that's a simplification because in most building types, the structure and the external cladding have got to be connected by some means. So you're going to have something that passes through there. And in some cases, the structure and the insulation zone are indeed one, particularly in timber frame buildings. So it's a simplification. These rules can be stretched or even broken, but this is the ideal, and it's good to understand this as a basic idea, as a guiding principle to how you develop your airtightness strategy. The next step is to develop that strategy in a joined up way. So you may have decided that you're going to have an airtight line with a certain material within your construction, but the real key question is, does it join up everywhere? Can you make that a comprehensive line around the entire section of the building? So joined up thinking through every section of the building. This is a more developed idea. So here's an airtight strategy for some student accommodation, and that airtight line goes all the way around. And we've started now to flesh out what that actually looks like in terms of materials and junctions and where they occur. And this kind of sketching allows you to just think these things through. And you might find exceptions. You might find areas where it doesn't quite join up, or the joint becomes more complex, and then you have something to resolve and to work through. But you also have to think in 3D. These images are a nice 2D section, but what happens in and out of the page, as it were, particularly where you have more complex structural elements that might form part of your airtight line and might interface with it. I wouldn't recommend this approach on any project with steel work that becomes part of the airtight line, but nevertheless, it's not unachievable if you're able to think through those junctions and come out with a strategy for how you're going to seal those elements. The key thing is you need to understand your building in 3D to do this job properly. Here's another example of some 3D thinking. So here on plan here, you can see this junction, and it all looks fairly straightforward On there, you've got tapes and various connecting membranes that go from this window around, following around the junction. But in reality, actually in 3D, this is more complicated, and there are elements within the window framing and the steelwork which needed thinking through in 3 dimensions. How would the EPDMs of these windows be connected around steels and so on? So a bit more thinking that we did around that, just to kind of prove that concept would work. Here's another example. This is a project in Oxford. It's a convent building, and we developed an airtightness strategy, which is basically on the outside of the blockworks. You can see the blue line here. So a Parge coat was applied to the outside of the blockwork, nice and easy airtight line, because none of the internal floors or walls would have any effect on that. Very simple to airtight detail the windows. The problem came at the eaves here, is how do we take that airtight line on the outside of the blockwork and transfer it onto the roof? The problem being that the roof timbers, the structure of the roof comes down on top of a plywood deck, and on top of internal timber structure on the inside of the building. So what we did here was we broke the plywood decking in the detail so that the airtight line could be lapped down onto the blockwork like so, to make that joint. That looks perfect in 2D. And indeed, we thought about the 3D nature of this, because you've also got timbers that are passing through this line here as well. They're going to need to be treated and taped where they pass through at this point. And that all seemed good, but when we got to site, there was a few things we hadn't anticipated. The one was being that the carpenters actually had quite a lot of freedom in the way that they constructed that roof and the ceiling inside that room. They added extra timbers to support the ceiling. They did things in a way that made it easy for themselves, but what, of course, they weren't thinking about or weren't aware of was the airtight implications. So rather than having a single timber come here through this point here that could be treated quite easily, we had multiple timbers passing through the same point, and you can see the gaps between those timbers and how those joints interact with our airtight line, and that becomes very complicated. So we had to work quite hard to get those treated. Our first air test was 1.5 air changes. Our target was 1. We managed to get it down to 1.3 with some work on these, particularly on these junctions, which was a really positive result. Not quite on target, but nevertheless a very airtight building. Not a passive house actually itself, but a really good result for that building. So air barrier types. There are lots of different materials you can use for air tightness. The key thing is to know that they are airtight. There's lots of membranes out there. There's materials like concrete, which are typically considered airtight, CLT, typically airtight. And there's lots of tried and tested materials. And that's the main thing I would say is, go for something which is well known to be a good solution for airtightness. The Passivhaus Trust has this chart on it, which is very helpful. It compares different types of air barriers and in terms of cost and technical aspects. Really helpful when thinking through that strategic decision. Things that are not so airtight would be some of your other building materials. Blockwork is well known to be not airtight. It sort of seeps air through it. Very hard to detect, but it does. Plasterboard, skims of plaster are not considered airtight, particularly because they tend to crack and have gaps. Generally speaking, timber is not considered airtight. If you have a lot of it, you're likely to see a lot of leakage through its surface. And then there are various products like some of the lower cost tapes, things like silicone and caulk. They're not really airtight, or at least they may start airtight, but they might shrink, crack, and they don't have the longevity that we would want for an airtight building. I'm particularly thinking in terms of moisture protection. You don't want something that gets worse over time, that could lead to moisture problems later in life of the building. So some examples of strategies. So for masonry, I mentioned earlier, a very common one, which is the Parge coat on the outside of blockwork, or indeed a full plaster finish on the inside. So traditional plastering is a very good airtightness layer. That's been done for quite a number of airtight buildings. This is another option which we've done on a few projects, which is to use a spread applied membrane on the blockwork on the inside and create that kind of airtight line internally. In this case, it was for each dwelling had its own sort of airtight line that was simply spray applied. A timber frame, very typically that would either be membranes or an airtight OSB. There are airtight OSB products that you can get. And that what we like about timber frame systems is they are indeed often a system. So timber frame system suppliers often have an airtightness sort of strategy built into what they've designed. So we like that about timber frame. Steel and concrete, very different sort of approach needed here, particularly around where you've got steel frame elements or SFS infill between concrete frames. We tend to here look at an external airtight line that is external of the structure, internal of the installation. So something like this is what we did on the UE project, where the airtight line is actually a membrane on the outside of the sheathing board on the inside of the insulation. So effectively the building is wrapped in this membrane, or in that case it was a spray applied membrane on the outside of sheathing boards. I've got a bit more to come on that later on. So in terms of products, the real important thing here is the longevity of the product, the quality of the adhesives, things that are going to last and do the job right. Tapes is a classic one. So a high performance tape is able to deal with things like differential movement. The adhesives on those tapes are excellent. It's really key to get the right products and make sure that they're used in the right way. Just a bit on sequencing. We've talked about kind of thinking in 3D, but the other aspect of thinking in 3D is to think about how things are going to be built. What's the build order of a particular construction detail? So this is an example here of a steel and masonry structure. So there are some steel elements within this masonry building. That creates an airtightness problem for us. Our airtight line on this building is actually inside of the blockwork. How do we treat around this steel? And when do we treat around that steel? We're going to have concrete planks lowered on top of those steels. The way what we came up with on this one was to have a membrane which sort of droops down on the outside of the top of the blockwork, can be dressed around the top of the steel like so, and then once the planks have been installed, that can be then wrapped back over the top. So you're kind of wrapping the ends of the planks. And then it can be brought back up the blockwork wall above as that's constructed. So that's a sequence that allows airtightness to be dealt with at that junction, which would otherwise be very difficult to make airtight. But it needs thinking ahead. It needs that kind of build sequence thinking through. Similar issue here. We've got an airtight line, which is the underside of these OSB boards, which are laid on top of these steels. And that creates some tricky junctions. We need to effectively bring the steels as part of that airtight line. We need to treat the steels where they enter the blockwork on the far side of the room. Again, sketching these things up, drawing them in 3D helps you to visualize and understand how the build order of this system. Most drawing work, let's face it, is still these days done kind of in 2D, at least in terms of the drawing that produced at the end, and you would not necessarily see these issues on a 2D detail. Windows and doors, I mentioned earlier, are imperfect by nature. There's no such thing as a completely airtight window, but what you want is a category 4 window for airtightness, or similar with a door. Maybe you might get away with a category 3 on some projects, but certainly not for all of your windows. You really want to go for 4. Even a 3, the full range of that, the lowest end of that is not particularly airtight. So we always say category 4 is the aim. And then, of course, you've got to connect your window and door to the main air barrier and make sure you detail that properly. Window doors also have imperfections when they're supplied to site. Don't assume that they are completely perfect, that they've been fully quality checked. Quality, of course, does vary, and you need to be aware of that. And you will pick these things up in air tests. So on the image on the left, there is a door where there's some sealant missing between 2 panels, and you can see light through there. And one on the right is similarly a door. It's a door joint, sliding doors, and you can see visible light through there where there's a piece of seal missing. These things need to be picked up as early as possible, and obviously manufacturers are responsible for ensuring their products are delivered to quality. Windows and doors and sealing them to the surrounding air barrier, there's different ways of doing that. Traditionally, in small scale passive house, that would be done with tapes. We come round to the view that particularly in larger schemes, EPDMs are at least as effective, and they're better known by trade. So on larger commercial scale projects, the window installers, they know EPDMs. A lot of windows have an EPDM fitting point, so they're ready to receive an EPDM. They're flexible, they're moldable, and the trades know them. The downside is that they're messy and sometimes unclear. So to know whether something is airtight, it's difficult to see with the kind of mess of the black adhesive to tell whether something is completely airtight. On an image on the right there, we detected some air leakage using ultrasonic leak detection. You wouldn't know that from looking at it. It's messy, it's not clear. So that's the downside. But we think overall this is a good way to go because of the familiarity with this system. On the other hand, tapes are really neat and clear. You know where the tape is. There's good techniques to get them well sealed around corners. However, they can have adhesion issues, particularly outside. They can be affected by weather. They can be a bit more tricky around things like bracketry. And on larger schemes, our concern is that they're not as familiar to the trades. So you're asking them to upskill. What you have to have reasons, I think, before you ask for a change of skill or new skills to be introduced. But I think they have their place. This is a large scale passive house scheme. You can see that's very neat, very clear, high quality tape products that we used on that project. Next, building services. There is huge risk with building services simply because there's the building services subcontractors are kind of further down the chain from the main contractor, and they may have their own subcontractors as well. So you've got potentially far less control over that work, even simple things like drilling holes for cable penetrations and things like that. So a few things that you can do to deal with this. One is to get a schedule of penetrations drawn up. Ideally, the contractor wants to take responsibility for that, get everyone around a table, understand where all the holes are going to be needed for building services. Think about spacing. The classic issue we see is that building services are not spaced out enough where they pass through the air barrier, making it impossible to fit grommets and tapes. Use the right products like a good proprietary grommet system or tape system, and then manage them on site. So having a system and process on site and just awareness on site of the responsibility for everybody to achieve airtightness. Typical penetrations would include things like external lighting cables, incoming services, typically through the ground, services entering through external walls. Your big one is going to be your handling unit or MVHR systems. None of these things are difficult to deal with, but they just need a bit of planning and identification and monitoring. Here's an example here of a drawing of a service riser. There's no real plan on this drawing for how these services will be made airtight, what they would be made airtight to. What we'd want to see here is a very clear air barrier that they are passing through, and then how they're going to be sealed to that air barrier, typically using these kinds of grommets or tapes. To do that, we know that they are airtight and they work, that they're relatively easy to install. If you don't do this, what you do end up with are these kind of situations here. So the one on the left is an air test we attended recently where there was a duct here, electrical duct going underground, and there was no ceiling of that duct. It was just an open duct going through to some external access hatch in the ground. During the air test, we found a significant amount of air streaming in from that duct. The one on the right is a similar issue with services, in that but in this case, these services have been sealed for fire. You can see the fire bat and the kind of adhesive filler used to fire seal surfaces, but actually they're not very well sealed. And during the air test, we found a lot of leakage at the back of those. What they needed was a proper airtight seal that went all the way around each of them. And there's a number of ways of doing that. So airtightness wasn't the target for that method. It was assumed that the fire stopping would do the job, but it didn't. Here's an example of a sketch where this sort of thing is being thought through. So you've got pipes and ducts passing through onto a roof, and there's separation between those ducts and pipes. There's grommets shown. It's this the sort of design development you want to see, and then this will of course allow you to then work out what's the total size of your services penetration on that roof, how much space is required to get all these services through, and also thinking about things like insulation, where does that stop and start, and so on. This is the sort of builder's work assessment that's needed for airtightness, and is important to follow this process on the design of building services. So site delivery, actually getting this done on site. One of the things we really see here that's quite clear is the fact that you have an air pressure test that's going to happen very late on site. It's an exam at the end of a project, and you don't know if you've passed until you get there. So there's a lot of risk hanging over contractors when they're being asked to deliver very airtight buildings. But that doesn't have to be the case. It doesn't have to be such a risky journey to that final air pressure test. There's quite a few things you can do along the way to reduce that risk and build confidence. So here's a few things that we typically see or would be indeed involved in producing. Reviewing the airtightness details, quite a fundamental one, depending on where you are in the project. Setting up a risk register and a penetration schedule so that you've actually got a way of being able to document and identify where those risks are going to be, and then have something to do about them. So don't assume that all your junctions are perfectly fine. Some of them are going to be more risky. There's going to be ones that are more difficult to execute, things that could go wrong if they're not spotted carefully on site. Get them on a risk register. Train your trades, give them toolbox talks specific to what they do that are around airtightness. Bring everybody on side so that everyone knows this is a joint effort, an important part of what the construction team are achieving together. Posters and signage are also part of that, so get this message out on site. I've got some examples of that in a minute. And lastly, an inspection and testing plan, and this really is the fundamental thing to building confidence. You're not waiting until that final air test to find out whether you've passed. You're doing early air tests, you're doing inspections, you're doing diagnostics to build confidence, so that by the time you get to that air pressure test, you know that you're going to be in a good place. An airtightness champion can be a really good way of helping to deliver all of this. This is a nominated person who is on site, and I mean literally they are walking around site regularly. They're not sat in the site office most of the time. They're involved at the front line of the construction, that they are able to take some responsibility of this. We like to have one person nominated for this because it gives someone a particular responsibility. Obviously, everyone should have some responsibility, but have someone who owns this issue and is able to then monitor specifically around airtightness across all the trades and all the works going on site. We think that's a really effective thing to do. Example of a risk register, penetration schedule, as I said before, getting details on to a register. Are they going to be a risk, and what do you do about it? What's the plan? Site awareness, so posters, anything to identify what is the airtight line, and any do's and don'ts on site. Just get that awareness going, combined with some toolbox talks. And then testing and inspection plans are really fundamental. Loads of aspects to these. You've got the air testing strategy up there on the right. You can see for a project where we developed an air testing strategy on different cores, how many air tests are going to be, where the blower doors, fans going to be mounted, how is that going to work, get an air test contractor support in that process and bring them on board. There's a lot more to be said on the ITP. I think diagnostic testing as well is quite fundamental, being able to get tests early on, But the point is to build a plan, is to make something, bring something together which maps out how you're going to achieve airtightness and build that confidence over time, and then to, of course, deliver it. Workmanship is fundamental to airtightness. The idea, of course, of a good design is that the workmanship levels are as low as they need to be, as low as they can be for delivery. If you can keep things simple and not require more skill to implement the tight line, you're more likely to be successful. But nevertheless, there are workmanship skills required, monitoring is required. And here's an example of taping techniques, for example. None of these things are difficult, but they're not all these skills are fully known. And sometimes there may be training of operatives. Here's an example of not so good workmanship. And this happens if there isn't a kind of awareness or training in these techniques. But I think fundamentally as well, it doesn't look like a particularly good detail. And that's the sort of thing we want to avoid. We want to avoid messy details like this. Is that airtight? It doesn't look it. Air test contractors, really fundamental part of this process to get a good air test contractor, someone who is going to support you in getting the result you want. You can pay very little for air test contractors to come to site for a few hours. It can be a very low cost, but you get what you pay for. And in our view, you need to think about the scope of that air test contractor very carefully. We think that the best thing is to get someone with experience, someone who has some construction knowledge, so they understand buildings generally, and hopefully this building in particular. Someone that's proactive. They haven't just come to kind of run the test, they've actually come to help you resolve problems. Thermography is a really key tool to help diagnose issues. You can see some images on the right there of an air test going on and a thermographic camera that's able to spot these leaks. And fault finding, that they're actually going to go out and find issues and help you resolve them. That, we would suggest, is worth the extra cost that it will bring, because you will end up having far less remedial work, fewer air tests potentially, and it pays for itself in the longer term. There are other inspection diagnostic techniques that we would deploy on projects trying to achieve this level of airtightness, and where they sit as well depends on what stage you are in the project. You want to try and do diagnostic inspections as early as possible to de-risk the project, but not all techniques are possible at that stage. But very early on, you can do visual inspections, and that's the most common thing you're going to be doing, checking the quality of airtightness, taping and seals, EPDMs, and so on. A new technology which we are very supportive of as a business is ultrasonic testing, which is a technique that allows you to detect air leaks much earlier on in the process of construction. And that can carry through to sort of mid-construction. But towards the end of construction or later stages, and as early as you can, pressure testing is the most effective way to identify leaks, measure the building's performance, and find issues to rectify. You want to try and do this as early as you can. The reality is, of course, that you can only do it when you have a building that's relatively well sealed. And so that's where the importance of these earlier diagnostic tools comes in. I mentioned the thermography and a pressure test. This is really fundamental. What you can see here is a pressure test where we depressurize the building, and cold air is being pulled in through the eaves in the stairwell. And this pattern is being created by the dart and dab behind the plasterboard. Quite an extraordinary airflow pattern that you're seeing, the temperature at the surface affected by that airflow. You would not have known that had we not had the thermographic camera. The actual air leak is in the eaves. The air was appearing in a cupboard on the ground floor, but this is the first floor in the eaves. So thermographic camera is far more revealing than simple air pressure testing or a smoke pen. It really allows you to see behind the layers of the building. I mentioned ultrasonic testing. So a particular product that we support is called the Porter scanner. And as I say, that can allow you to detect air leakage through a building without having to pressurize it. No temporary sealing. You don't have to stop work. You can use that to find faults really early on in construction. As soon as a bit of your air barrier is complete, you could use the portal scanner to check it, to test it. So in summary, airtightness is an issue for energy, for comfort, and for protecting the building fabric. The mindset you need to have is one of zero air leakage. We're targeting zero in our design, knowing that that's the only way to deliver the sort of airtightness that you would get for a high performance building. The formula for airtightness is the combination of that robust design, checks those boxes in terms of the quality of that design, and then the workmanship on site to deliver that. You need strategy. You need to have a plan that's clear and joined up. You need to think in 3D. Airtightness isn't a 2D section issue. It's the full 3 dimensions of your air barrier, and it's often intersected by things like structure and so on. You need to think about materials and products. You need the right materials, choose them carefully, and then choose high quality products that work with those materials. Building services is a common issue with airtightness, but it can be managed. It can be managed through simply documenting penetrations, challenging designs, making sure there's spacing for services, and then monitoring the installation on site and bringing everybody on board through toolbox talks and informing people on site of the issue of airtightness. Inspection and testing plans are really fundamental to delivery of airtightness, and they set out how you're going to do early stage diagnostics, how you're going to monitor quality, and finally do the airtightness testing of the building itself. And lastly, there are new techniques around, including ultrasonics, which are making this easier and helping to really de-risk achieving this sort of airtightness in high performance buildings. Thank you very much. Are there any questions?